Hello, my name is Atanilson, and today we are gonna dive into the fascinating world of derivatives. In my opinion, probably one of the most useful concepts in math. Derivative is a key concept within calculus, which dates back thousands of years, with many contributors. However, the people that are widely recognized for the invention of calculus are Isaac Newton and Gottfried Leibniz for their contribution in differential and integral calculus, respectively. In terms of differential calculus, Isaac Newton is widely recognized for his foundational contribution. He introduced ideas like product rule and chain rules. He basically developed derivative-based reasoning out of necessity in order for him to have the tools he needed in order to describe the laws of motion. In order for us to describe how things are changing, for example, how an apple velocity is changing, we need derivatives, which is the rate at which a quantity changes with respect to the other. Geometrically, derivative is the slope of the curve at end point, and the process of finding the derivative is called differentiation. Let's take an example. How would you say this function is changing over time? You'd probably say it doesn't change, which is correct. But mathematically, how do we describe that? In order for us to define mathematically, we would need the slope under the curve, which is given by delta y over delta x. Replacing the values at 2 points, we would have our answer as equal to 0. Now, if we have a line instead, the definition of the change would not change. We still have the slope, and replacing at endpoint, for example, x equal 1, x equal 2, we would have that it's equal to 1, and the slope at a straight line doesn't change at endpoint. Now, let's say we have a more complicated function. We still have the slope, and as per definition, the change of the function can be found by the slope of a straight line. But which straight line? That's where we introduce the concept of the tangent line. We compute a tangent line and we find the slope. However, how exactly do we compute this tangent line? In order for us to compute the tangent line, let's try to plot a normal line that passes through x and x plus h. Finding the slope of that line, delta y over delta x, we will have y at x plus h minus y at x, and the denominator, the x, cancels out and we have over h. Now, if you notice, if we change the h to a smaller value, it will get closer to the tangent line. Okay. Now, as h gets smaller and smaller, it will eventually be equal to the tangent line. So we can say that our dy over dx is the slope of that line as h tends to 0, which is basically our definition of the derivative. And this derivative represents how the function instantaneously changes with respect to x. Okay, now you'll find main notation of derivative f prime x, y prime, dy dx, dfx, and so on, but all of those mean exactly the same thing. Okay, now let's go for an example. Let's say you want to find the speed at which you are traveling at this roller coaster when t is equal to 5. For simplicity, let's say the function is given by t squared. If we replace this function at our formula, when we replace it when h tends to 0, we're gonna have that our derivative is 2t, and replacing the value of 5, we're gonna have the change in distance with respect to time at t is equal 5 is equal to 10. And of course, you're not gonna have to go through the process we just went through, because there are many rules that we can apply when we have a function. We have the constant rule, which says the derivative of constant is equal to 0. We have the power rule, we have the sum rule, we have the product rule, we have the quotient rule, and we have the chain rule. All these tools we can use to find the derivative of complex functions. Derivatives have many applications. We can apply in physics for the laws of motion, in chemistry to find how a reaction changes over time, in biology to track population growth, and in many other fields, in economics, how the company is growing, environmental science to calculate the rate of pollution, and even in machine learning where we can use to optimize our models. Basically, to summarize, wherever there is change, there is derivatives.